When a user opens Yelp or Google Maps to find the best coffee nearby, they are pinging a proximity service. Designing the system requires handling massive concurrent localized queries across millions of data points. Looking at this interface from Yelp, the functional scope is clear. The system must return businesses based on a user's latitude, longitude, and search radius. It also needs to provide business owners with the ability to add, update, or delete their listings. This document outlines the non-functional constraints. The system has to deliver low-latency responses so users see nearby locations quickly. Furthermore, because we are processing user location data, strict adherence to privacy laws like GDPR and CCPA is non-negotiable, alongside high availability and scalability requirements. The search radius itself is a variable constraint, adjustable by the user anywhere from half a kilometer up to 20 kilometers. On the business owner side, updates do not require strict real-time consistency. If a restaurant updates its hours, we can agree that the change takes effect by the next day without breaking the user experience. These parameters dictate the entire architecture. We have to serve hyper-local searches at lightning speed, while write operations can tolerate significant delay. To size the system, we assume a baseline of 100 million daily active users, querying against a total pool of 200 million business listings. This calculation breaks down the expected load. If each of those 100 million users makes 5 searches a day, divided by roughly 100,000 seconds in a day, the system must handle an average of 5,000 search queries per second. Compare that 5,000 queries per second to the write volume. Businesses rarely change their names, addresses, or operating hours. Therefore, the system's storage and caching layers must be heavily optimized for read throughput, safely deprioritizing write consistency. This is a strictly asymmetric workload. Reads and writes must follow different architectural paths to prevent resource contention. A standard monolithic architecture routing all operations through a single database instance will simply collapse under the sheer volume of read requests. Here is the baseline REST API contract. We have a GET endpoint for searching nearby locations based on coordinates and radius, along with standard POST, PUT, and DELETE endpoints for managing the business metadata. This table shows a straightforward relational data schema using a database like MySQL. It stores the business details, relying specifically on latitude and longitude fields to represent location. In this initial model, latitude and longitude are stored simply as decimal numbers. Because write operations are infrequent, we do not require the massive write throughput capabilities of a NoSQL engine like Cassandra here. A relational database handles the low-frequency updates efficiently. The business table relies on the business ID as its primary key, making exact point lookups fast and straightforward. While this schema handles metadata effortlessly, the real test is how it processes a distance-based search query using only these numeric latitude and longitude fields. To find nearby businesses in this relational model, you have to query a square boundary. You draw a bounding box using the user's coordinates and ask the database for any rows where the latitude is between 2 values and the longitude is between 2 values. Proposing a full table scan to evaluate every coordinate pair for 200 million businesses will result in an immediate rejection. Adding standard B-tree indexes to the latitude and longitude columns does not solve the issue.
A B-tree index can only efficiently optimize a search along a single dimension at a time. This visualization highlights the intersection problem. The database pulls a massive dataset of all businesses within the latitude range, pulls a second massive dataset for the longitude range, and then attempts to intersect them in memory. At 5,000 queries per second, forcing a database to compute these massive intersections will max out CPU and network bandwidth almost instantly. Since a standard index cannot bridge these 2 dimensions effectively, we need a method to compress that spatial information into a single indexable value. This requires a specialized geospatial indexing strategy, utilizing algorithms like GeoHash, Quadtrees, or Google S2 to represent grid areas as single searchable strings. Spatial search inherently evaluates 2 axes simultaneously. Only by flattening that geography into a single index dimension can a database retrieve the proximity data efficiently. This diagram shows the architectural solution, decoupling the workload between a location-based service, or LBS, and a dedicated business service. A load balancer acts as the entry point, automatically distributing incoming traffic based on the URL path. Search requests are routed to the LBS, while crowd operations go to the business service. The LBS absorbs the intense read volume. It is designed to be completely stateless, allowing the system to horizontally scale by simply adding more servers during peak hours. At the storage layer, a primary-secondary setup isolates the workloads. Write traffic from the business service hits the primary database. The heavy volume of read queries from the LBS is distributed across multiple read replicas. Because the business updates replicate asynchronously, there will be a slight delay. This eventual consistency is a highly acceptable trade-off for a product where business details rarely change by the minute. By decoupling the pathways, a massive spike in user search traffic will never consume the resources required to process incoming business data. This is the final execution flow. To further eliminate database latency, the architecture introduces specialized Redis clusters, one to cache geohash indexes, and another to cache the fully hydrated business info objects. When a client sends a search request, the LBS evaluates the user's location and the requested search radius to determine the precise geohash length required for the query. To prevent boundary issues, where a user might be standing on the edge of a grid cell while the closest restaurant is just across the line, the LBS calculates the neighboring geohashes to ensure complete coverage. The service then makes parallel calls to the geohash Redis cluster, instantly retrieving all business IDs located within those specific grid cells. Armed with the precise IDs, the LBS queries the business info Redis cache to pull the actual details, names, addresses, and ratings, without ever touching the primary database. The LBS calculates the exact distances from the user, ranks the businesses accordingly, and returns the final JSON payload to the client. This diagram illustrates the geographic advantage of this design. Deploying these LBS clusters and Redis caches into multiple global regions physically positions the computation closer to the user, strictly minimizing network latency. A proximity service operates under extreme asymmetric pressure. By combining stateless read pathways, plus asynchronous database replication, and one-dimensional spatial indexing, the architecture handles millions of localized queries while maintaining sub-second latency and high availability.